From the earliest days of human thought, certainty was considered the highest virtue. To understand the world was to define it, to label it, to declare truth with confidence. Yet the story of science is not one of unwavering certainty, but of relentless correction. Every breakthrough in our understanding of the universe began as a confession of ignorance. Every discovery that reshaped human knowledge started when someone dared to say that the old answers were wrong. In ancient Greece, Aristotle looked to the heavens and described a cosmos of perfect circles. He imagined Earth at the center, motionless and noble, while celestial spheres revolved in orderly harmony. It was an idea both elegant and intuitive. For nearly 2,000 years, the geocentric universe remained unchallenged, woven into philosophy, religion, and daily life. To question it was to question order itself. Yet as careful observers began to measure the motion of planets, they saw something unsettling. The planets did not move as they should. Their paths wandered backward, looping across the sky in retrograde motion. Claudius Ptolemy, centuries after Aristotle, sought to preserve Earth's central throne by inventing a complex system of circles within circles. It worked as a mathematical trick, but did not reveal the truth. The system predicted motion but hid meaning. It took Nicolaus Copernicus, in the 16th century, to propose the unthinkable that Earth itself moved. His model was not perfect. It still relied on circular orbits and could not fully match observation. But it began a revolution, not of astronomy alone, but of thinking. When Galileo Galilei later turned his telescope toward the heavens, found mountains on the moon, moons around Jupiter, and imperfections in the supposedly perfect sky, his discoveries shattered the philosophical comfort of a stable universe. This was not merely a change of models, it was a change of mindset. For the first time, science demanded that nature, not authority, decide what was true. The telescope became a weapon against dogma. When Johannes Kepler replaced circles with ellipses and Isaac Newton revealed that one set of laws could govern both falling apples and orbiting planets, humanity stepped into a new understanding, one that united heaven and earth under the same physical rules. Newton's universe was precise and predictable. It was a clockwork cosmos, ruled by mathematical certainty. His laws of motion and gravitation explained tides, planetary orbits, and the structure of the solar system with astonishing accuracy. For more than 2 centuries, scientists and philosophers believed they had found the final truth. Everything from cannon fire to the dance of comets could be derived from Newton's equations. Determinism became the creed of reason. If one knew all the forces and positions of every particle, one could, in principle, predict the future forever. The universe appeared complete, vast, mechanical, and absolute. Yet certainty, once again, proved temporary. In the late 19th and early 20th centuries, cracks began to appear in the edifice of Newton's world. Light, that most familiar of phenomena, refused to behave as it should. When James Clerk Maxwell united electricity and magnetism, his equations described waves that moved at a fixed speed, the speed of light. But fixed according to what? If light moved at the same speed for all observers, Newton's laws could not hold. Something deeper had to give way. Albert Einstein, in 1905, offered a new foundation. Space and time, once absolute, became relative. His special theory of relativity dissolved the notion of universal simultaneity, showing that time itself bends and stretches depending on motion. A decade later, his general theory of relativity transformed gravity from an invisible force into the curvature of spacetime. The very geometry of the cosmos was alive and dynamic, capable of bending under the weight of energy and mass. Newton's certainty had been replaced by Einstein's elegance. A vision united geometry and gravity, but demanded humility from those who sought eternal truths. Einstein's work did not invalidate Newton's. It absorbed it as a special case, valid where gravity is weak and speeds are low. But in the extremes near black holes, or across the vastness of the cosmos, Newton's laws failed. Each new discovery thus became not a contradiction of the past, but a refinement of it. The process of being wrong was not a flaw in science, it was the essence of science itself. Then came an even greater disruption. While relativity reshaped our view of the large-scale universe, another revolution emerged in the microscopic world, quantum mechanics. The realm of atoms refused to obey the logic of everyday experience. Particles behaved as waves, waves acted as particles, and outcomes existed only as probabilities until measured. The classical notion of cause and effect shattered. Einstein himself resisted this indeterminism, insisting that God does not play dice with the universe. But experiments proved otherwise. Quantum mechanics, though philosophically unsettling, became the most accurate theory in the history of science. By the middle of the 20th century, physics had split into two magnificent, yet incompatible theories. General relativity described the cosmos at its largest scales: galaxies, black holes, and the curvature of spacetime. Quantum mechanics described the smallest particles, atoms, and fields of energy. Both were correct within their domains, yet they could not coexist within a single framework. The unification of these two pillars remains the deepest challenge in modern physics. This pattern confidence followed by collapse, certainty replaced by a deeper uncertainty, is not a story of failure, it is the rhythm of discovery. Every time humans believed they had reached the truth, nature revealed new complexity. What was once unthinkable became obvious, and what was once obvious became obsolete. To be wrong was not to lose, but to learn. Science, unlike belief, does not demand permanence. It demands revision. Its power lies not in declaring truth, but in surviving correction. The philosopher Karl Popper formalized this idea in the 20th century when he argued that scientific theories can never be proven, only falsified. A good theory is not one that claims certainty, but one that can be tested and potentially disproven. Truth, in this view, is provisional, a horizon that recedes as we move toward it. This humility is not weakness, it is the strength of the scientific method. To be wrong is to evolve. To doubt is to progress. The universe does not change when we are mistaken, only our understanding does. From the fall of geocentrism to the rise of relativity and quantum mechanics, each revolution in thought was born from error, refined by skepticism, and validated by evidence. If our greatest leaps have come from our greatest mistakes, perhaps today's understanding of the universe is just another step toward being wrong again. What we call truth may simply be the next approximation, a fleeting alignment between our models and reality, before a new discovery bends the picture once more. The realization that all scientific truth is temporary marks one of the most profound shifts in human thought. It means that every equation, every principle, every cosmic model is only a map and not the territory itself. The maps grow more precise, but the terrain remains infinitely more complex. In every age, the scientific mind must face the same paradox. We understand the universe better than ever before, and yet we remain surrounded by mystery. When Newton unified the motion of planets and falling apples, he could not know that his concept of gravity would one day break under the strain of extreme space and time. When Einstein reimagined gravity as the curvature of spacetime, he could not have foreseen that his own equations would predict singularities, regions where physics itself ceases to function. And when quantum mechanics arose, no one could have imagined that its mathematics would become the foundation of technologies like semiconductors, lasers, and magnetic resonance imaging. Each revolution began not from certainty, but from the discomfort of contradiction. The scientific method thrives in that discomfort. It is built on observation, hypothesis, experimentation, and replication, a self-correcting cycle that weeds out illusion. The process is indifferent to pride or belief. It cares only for what can be measured and verified. When Galileo dropped spheres from the Tower of Pisa, when Maxwell built his electromagnetic theory, when Edwin Hubble found that galaxies were rushing away from us, each discovery forced a re-evaluation of what was thought to be unshakable. Knowledge grew not from agreement, but from the relentless testing of doubt. Consider the lesson of Hubble's discovery. Before 1929, the universe was thought to be static, an eternal stage upon which stars burned and died but never drifted apart. Einstein himself introduced the cosmological constant to preserve this stability in his equations. Yet Hubble's observations of galactic redshifts revealed that space itself was stretching galaxies, were not simply moving through space. Space was expanding between them. Einstein's greatest blunder, as he called it, was not his mathematics, but his assumption that the universe must conform to human intuition. The cosmos was not static. It was dynamic and restless, growing larger every moment. The story repeated in countless forms. Each time humanity built a perfect theory, reality revealed its imperfections. In the 19th century, physicists believed they had solved nearly all major problems of science. Then came the ultraviolet catastrophe, black-body radiation, and the photoelectric effect phenomena that classical physics could not explain. These anomalies led to quantum theory, which in turn redefined energy, matter, and even causality. Every step forward began with an observation that refused to fit the model. Science advances not by confirming what we expect, but by confronting what we cannot explain. This is why anomalies, the subtle mismatches between theory and evidence, are treasures, not threats. They point to the edges of understanding, the cracks through which new ideas enter. The discovery of Neptune, for instance, came from the irregular motion of Uranus. The discovery of cosmic expansion came from unexpected redshifts. Even the birth of quantum mechanics began with the failure of classical thermodynamics to describe light. To be wrong in science is to be standing on the threshold of a deeper truth. But being wrong in science does not mean inventing fictions. It means refining approximations. Every scientific theory is an approximation of reality that works within certain limits. Newton's laws still guide spacecraft across the solar system. Relativity refines them, not replaces them. Quantum mechanics extends our reach into the atomic and subatomic, but it too is bounded by the scale at which gravity becomes strong. Science is not a series of discarded truths. It is a hierarchy of increasingly accurate models. Even the philosophical foundation of science recognizes this fluidity. The concept of provisional truth is central to how scientists interpret evidence. It accepts that all knowledge is conditional, that certainty exists only within the boundaries of measurement and experiment. A theory is not an eternal truth. It is a working description, awaiting the next generation of instruments and minds. The telescope, the particle accelerator, the gravitational wave detector, each tool peels back another layer, exposing new questions beneath every answer. This humility separates science from belief systems that seek permanence. Religion, ideology, and superstition anchor themselves to unchanging truths. Science survives by letting go. The moment a theory refuses to be tested, it ceases to be science. The philosopher of science, Thomas Kuhn, described this process as a series of paradigm shifts, moments when the prevailing framework collapses under the weight of contradiction and a new one rises in its place. Copernicus replaced geocentrism, Newton replaced Aristotelian physics, Einstein replaced Newton. Each transition was not a rejection of reality, but a recalibration of perception. Still, these revolutions came at a cost. Every shift forced humanity to surrender a piece of its comfort. The Earth was no longer the center of creation. The universe was not mechanical, but relativistic and curved. Matter was not solid, but mostly empty space, filled with probabilities. At each step, the cosmos became less intuitive and more alien. Yet the reward was clarity, the realization that our understanding grows only when we abandon the illusion of completeness. To be wrong is to be human. To correct that wrongness is to be scientific. The evolution of physics, astronomy, and cosmology over the last 2,000 years is not a march towards certainty, but a spiral of ever-deepening questions. Every generation rewrites the universe with finer precision, knowing full well that its truths will one day be rewritten again. The willingness to embrace that endless correction defines the modern scientific spirit. Knowledge, in this light, is not a monument, but a journey, a continuous motion toward better understanding, guided by evidence and anchored in humility. As the historian of science, Jacob Bronowski once said, "Science is a tribute to what we can know, although we are fallible." And so, the history of being wrong is not a story of error, but of progress. From Aristotle's perfect heavens to Einstein's curved spacetime, from Newton's clockwork to quantum uncertainty, The path of discovery is paved with the ruins of former certainty. The greatest minds in history were not those who claimed to be right, but those who recognized where they were mistaken. Every discovery in science is a confession that we did not know as much as we thought. The deeper we look, the more our explanations begin to dissolve into new questions. This is not a failure of science, but its defining strength. It survives by admitting ignorance. The moment we claim to have reached the end of understanding, we begin to move backward. Progress depends on the ability to say that something once believed true was never true at all. The fall of geocentrism is only one example among countless others. In biology, the idea of spontaneous generation, that life could arise from non-living matter, held sway for centuries until Louis Pasteur's meticulous experiments in the 19th century closed that door forever. In geology, the Earth was once believed to be a few thousand years old. Now, radiometric dating reveals a planet more than 4.5 billion years in age. In astronomy, the Milky Way was once thought to be the entire universe, until Edwin Hubble's measurements in the 1920s showed that countless other galaxies stretched beyond it. Every time we expanded our methods of measurement, the scale of the universe and our place within it changed. Science has never moved in a straight line from ignorance to enlightenment. It has advanced through cycles of disruption. Each generation inherits models that seem flawless, only to find cracks when new instruments or ideas expose what was previously invisible. The microscope, the telescope, the particle accelerator, each was a lens through which humanity glimpsed the inadequacy of its own knowledge. The more we refine our tools, the more the universe reveals its complexity, and every refinement forces us to discard an older certainty, to rewrite the boundaries of truth. The great revolutions in thought were rarely comfortable. When Charles Darwin published On the Origin of Species, he did more than describe evolution. He challenged the belief that life was fixed and unchanging. His theory did not diminish humanity. It placed us within the same natural processes that shaped all species. Yet the backlash was immense. The idea of being wrong about human uniqueness felt unbearable. And yet, over time, evidence accumulated until the resistance gave way. The fossil record, genetic sequencing, and observed adaptation all confirmed Darwin's central insight. Being wrong had once again made the world more comprehensible. This pattern persists even today. Modern cosmology, for all its triumphs, rests on assumptions that may one day collapse, just as surely as geocentrism or the clockwork universe did. We speak confidently of dark matter and dark energy, yet these are placeholders, names for phenomena we cannot yet explain. We trace the universe back to the Big Bang, yet we cannot say what came before or what caused it. Each frontier of knowledge pushes us to confront the edges of our own ignorance. That confrontation is not weakness, it is the reason science continues to evolve. The philosophy of provisional truth lies at the heart of this process. To be provisional means to accept that every model of reality is temporary. It does not mean that truth is relative, but that our grasp of it is incomplete. The laws of physics are not wrong because they change. They change because they become more precise. The motion of planets is still governed by gravity, but our understanding of that gravity deepens with each discovery. The equations of Newton remain true within their limits. Einstein's relativity refines those limits, and future theories will refine them again. This constant revision is not instability, it is progress measured in humility. Throughout history, every claim to absolute knowledge has eventually been overturned by observation. The philosopher of science Karl Popper reminded us that scientific theories must always be falsifiable, meaning that they can, in principle, be proven wrong. This openness to being disproven is what separates science from belief. It demands that even the most elegant idea be subjected to experiment and observation. When evidence contradicts it, the idea must yield, no matter how beautiful or beloved it is. To live within this framework is to embrace uncertainty as a natural state. Scientists do not seek final answers, they seek better questions. The universe is not obliged to fit our expectations, and history has shown that it rarely does. Each discovery reveals not a destination, but a new horizon. The astronomer who measures distant galaxies, the physicist who studies particles, the biologist who maps genomes, all are participating in the same ancient rhythm of correction. To know more tomorrow is to admit what we were wrong about today. This humility has given humanity its greatest strength. It has led to the eradication of diseases, the exploration of space, and the creation of technologies that once seemed impossible. Yet it has also taught us a moral lesson that certainty is dangerous. When people believe they possess the final truth, progress stops. Dogma replaces curiosity. The courage to be wrong is the courage to remain open, to let the universe surprise us again and again. The history of being wrong is therefore the history of growth. From the first philosopher who watched the sky to the modern physicist probing the quantum realm, the pattern remains unchanged. Each discovery is an act of surrender, a recognition that nature, not human belief, dictates the rules. The universe is not obligated to make sense to us, yet through doubt and correction, we slowly learn its language. If our greatest leaps have come from our greatest errors, and perhaps today's understanding of the universe is only another step toward being wrong once more. The questions we now ask about dark matter, dark energy, and the fabric of space-time may one day seem as naive as the questions of Aristotle or Ptolemy. But that is the beauty of science. Every truth we hold today is a doorway to the next mistake, and through those mistakes, we move ever closer to understanding. If the path of knowledge is built upon correction, then the universe we describe today, its origins, its composition, its expansion, is not the final word. The standard model of cosmology stands as our best explanation so far, a framework of equations that fits the evidence with exquisite precision. Yet beneath its success lies an uncomfortable truth. Most of the universe it describes remains unseen. At the heart of modern cosmology lies a model that explains nearly everything we can observe and yet leaves almost everything unexplained. It is called the lambda-cold dark matter model, often written as WILCDM. This framework, built upon Einstein's general relativity and the accumulated evidence of the 20th and 21st centuries, describes a universe born in a hot, dense state that has been expanding and cooling for nearly 14 billion years. It tells us how galaxies formed, how cosmic structures evolved, and how light from the earliest moments still fills the sky. It is the most successful cosmological model ever created. Yet, it is also one of the most incomplete. The story begins with a single insight that the universe is expanding. In 1929, Edwin Hubble observed that galaxies are moving away from us, and that their speeds increase with distance. The light from these galaxies appeared stretched toward the red end of the spectrum, a phenomenon known as redshift. The simplest explanation was that space itself is stretching. What had once been a static, eternal cosmos was now revealed as dynamic and evolving. When the equations of general relativity were applied to this discovery, they predicted that the universe must have begun from a state of extreme density and temperature, an origin event we now call the Big Bang. Evidence for this explosive beginning accumulated over decades. In 1965, Arno Penzias and Robert Wilson detected a faint microwave signal coming from every direction in the sky. It was not interference, but the afterglow of creation itself, the cosmic microwave background, a relic of the moment when the universe first became transparent to light, roughly 380,000 years after its birth. Its nearly uniform temperature, only a few millionths of a degree Celsius apart across the entire sky, confirmed that the universe began as a nearly homogeneous sea of radiation and matter. Further evidence came from the abundance of light elements. Hydrogen, helium, and trace amounts of lithium observed in the cosmos matched the predictions of nuclear reactions that occurred in the first few minutes after the Big Bang. This alignment between theory and observation established the Big Bang as the foundation of modern cosmology. Yet as the universe continued to expand, gravity began to sculpt matter into stars, galaxies, and clusters, forming the large-scale structure we see today. Einstein's general relativity provided the mathematical foundation for describing this cosmic evolution. It showed that space and time are woven together into a single fabric space-time, and that the geometry of this fabric is curved by the presence of mass and energy. On the largest scales, the universe could be treated as a smooth fluid, expanding according to equations derived from Einstein's field equations. These equations link the rate of expansion, described by the Hubble constant, to the total energy density of the cosmos. If the density were high enough, the universe would eventually stop expanding and collapse. If it were too low, expansion would continue forever. But when astronomers compared the amount of visible matter, stars, gas, dust, to the gravitational effects they observed, the numbers did not match. Galaxies rotated faster than they should have. Clusters of galaxies exhibited gravitational binding that exceeded what their visible mass could provide. The universe seemed to contain far more matter than could be seen. To reconcile observation with theory, scientists introduced the idea of dark matter, a form of mass that does not emit or absorb light, yet exerts gravitational pull. Even with dark matter included, another puzzle emerged. In the late 20th century, astronomers studying distant Type Ia supernovae stellar explosions, so bright they can be seen across billions of light-years, found that the expansion of the universe is not slowing down, as gravity would suggest, but accelerating. Something unseen was pushing galaxies apart with increasing speed. To account for this, cosmologists revived Einstein's cosmological constant, representing a form of energy inherent to space itself. This became known as dark energy. The combination of these components, normal matter, dark matter, and dark energy, formed the lambda-cold dark matter model. In this framework, the symbol lambda represents the cosmological constant, or dark energy, while cold dark matter refers to slow-moving, non-relativistic particles that interact only through gravity. Observations from the cosmic microwave background, galaxy surveys, and gravitational lensing have all confirmed that this model describes the universe's large-scale structure with remarkable precision. Yet the precision of the model hides its profound mystery. The equations fit the data perfectly, but their ingredients remain unknown. According to the best measurements, only about 5% of the universe is made of ordinary matter atoms that form stars, planets, and life. About 27% is dark matter, invisible, yet gravitationally dominant. And roughly 68% is dark energy, a force that drives cosmic acceleration. In other words, 95% of the universe is made of something we cannot see, detect, or explain. This is both a triumph and a warning. The lambda-cold dark matter model works because it describes what we observe, not necessarily because we understand what it means. Each of its parameters, the densities of matter and energy, the rate of expansion, the curvature of space, is carefully adjusted to match observation. But these parameters do not emerge from first principles. They are inserted by necessity. The model is not an explanation of why the universe behaves as it does, but a mathematical summary of how it behaves. Cosmic inflation, for instance, was introduced to explain why the universe appears so uniform on large scales and why it is geometrically flat. It proposes that a fraction of a second after the Big Bang, space expanded exponentially, smoothing out irregularities. The concept fits the data beautifully, but the physical mechanism behind it remains unverified. A hypothetical field that drove inflation, called the inflaton, has never been observed. Inflation explains much, but it is still an assumption awaiting confirmation. The same uncertainty applies to dark energy. While the cosmological constant fits the observations, its origin is deeply troubling. Quantum field theory predicts a vacuum energy density 120 orders of magnitude larger than what is observed. This discrepancy, known as the cosmological constant problem, the largest mismatch between theory and measurement in all of science. It suggests that our understanding of space, time, and quantum physics is incomplete at a fundamental level. And yet, despite these gaps, the lambda-cold dark matter model continues to succeed. Observations from the Planck satellite, mapping the cosmic microwave background with exquisite precision, have confirmed its predictions to within a fraction of a percent. The distribution of galaxies, the formation of cosmic filaments, and the behavior of gravitational lensing all align with its framework. It is a model that describes nearly everything we can see, even as it conceals what we cannot. To many cosmologists, this duality of accuracy and ignorance defines the beauty of modern physics. It is a reminder that explanation and description are not the same. The model gives us predictive power, allowing us to calculate how structures form and evolve. But it does not tell us what dark matter is, or why dark energy exists, or whether space-time itself has a deeper origin. The standard model of the universe like every model before it, stands as a monument to both our knowledge and our limitations. It marks how far observation and mathematics can take us, and how much further nature still extends beyond our reach. If the equations match the evidence, yet 95% of the universe remains invisible, we must ask, can a model built on the unseen truly be complete? The standard model of the universe rests on a remarkable tension. It works so well that it conceals how little we understand. The equations describe how galaxies form and how light moves through expanding space, but behind the mathematics lie unknowns that stretch the imagination. The very success of the lambda-cold dark matter model may be a symptom of its incompleteness. It fits the data with extraordinary precision, but the entities it depends on, dark matter and dark energy, remain invisible. They are not confirmed particles or forces. They are names for phenomena we do not yet comprehend. When scientists speak of the standard model of particle physics, they refer to an experimentally verified framework that describes the known building blocks of matter and their interactions. The cosmological standard model is different. It is based on observation and inference rather than direct detection. The cosmic microwave background, large-scale structure, and supernova measurements all point to a universe dominated by something we cannot see. Yet, these same observations do not tell us what those invisible components are. The model's predictive power lies in its ability to describe motion and structure, not in revealing the true nature of reality. To understand why this matters, one must look at how the model came to be. Its foundations are mathematical rather than physical. Einstein's general relativity gives the geometry, quantum field theory provides the energy fields, and observation determines the constants. The cosmological constant, the Hubble parameter, and the matter densities are not derived from deeper laws. They are adjusted so that the model matches the data. In that sense, cosmology has become a science of fitting curves. Each new measurement refines the parameters, but the underlying mechanism remains hidden. The lambda-cold dark matter model also assumes that the universe is homogeneous and isotropic on large scales, that is, the same everywhere and in every direction. This assumption, known as the cosmological principle, is supported by the nearly uniform cosmic microwave background. But it may be an approximation rather than an absolute truth. On smaller scales, matter clumps into galaxies, filaments, and voids. The universe is not smooth, but laced with structure, and whether that structure influences the global expansion is still debated. Another tension lies in the value of the Hubble constant, the rate at which the universe expands today. Measurements based on nearby supernovae and Cepheid variable stars yield a value higher than that derived from the cosmic microwave background. This Hubble tension may be a statistical anomaly, or it may signal that our model is missing something fundamental. Some physicists suggest that dark energy could evolve over time rather than remain constant. Others propose new physics beyond the standard model, perhaps involving interactions between dark matter and dark energy. None of these possibilities have yet been confirmed. What is certain is that the lambda-cold dark matter model is descriptive rather than explanatory. It tells us what happens, not why. It does not explain why the laws of physics are fine-tuned to allow a universe that can form galaxies, stars, and life. It does not reveal why the cosmic density is so precisely balanced that the universe neither collapses nor expands too rapidly. It does not show why quantum fluctuations in the early universe produced just the right amount of irregularity to seed galaxies billions of years later. These coincidences could be the result of deeper physical principles, or they could be evidence that the model is only a temporary scaffold. For now, it remains the best framework we have. Its power lies in its capacity to predict. Using the lambda-cold dark matter equations, cosmologists can simulate the evolution of the universe from a fraction of a second after the Big Bang to the present day. These simulations produce a cosmic web strikingly similar to what telescopes observe. clusters connected by filaments of dark matter, with galaxies forming at their intersections. The success of these models demonstrates that gravity and expansion, as described by general relativity, can reproduce the universe's structure on the largest scales. Yet the model's elegance also hides the depth of its mystery. Consider what it implies. Almost all the mass and energy in the universe come from substances or processes we have never directly observed. Dark matter makes galaxies spin the way they do, but it passes through ordinary matter without resistance. Dark energy stretches space itself, but it cannot be detected by any known experiment. These components are inferred only because, without them, the equations do not work. The model depends on invisibility to hold its shape. This reliance on the unseen raises a philosophical question. At what point does fitting the data become a form of belief? Science advances by testing what it cannot yet explain, but when evidence is indirect, the line between theory and assumption becomes delicate. Cosmologists are acutely aware of this. They do not claim that dark matter and dark energy are proven entities. They call them placeholders, working names for missing pieces of a larger puzzle. Their existence is supported by observation, but their nature remains an open question. Despite these uncertainties, the lambda-cold dark matter model unites nearly a century of discoveries. It connects the redshift of galaxies with the relic radiation of the cosmic microwave background, the clustering of galaxies with the ripples imprinted in early space. Every new telescope, from the Hubble Space Telescope to the James Webb Space Telescope, adds precision to the picture, refining the parameters that describe our cosmic history. Each observation, in turn, strengthens the model's predictive power, while reminding us that understanding and accuracy are not the same. The challenge now is to move from description to comprehension. What is dark matter made of? Why does dark energy dominate the universe? And are these two phenomena connected, or are they entirely separate mysteries born of the same incomplete understanding? The answers will not come easily. They will require new instruments, new theories, and perhaps a willingness to question the very foundations of relativity and quantum mechanics. For all its success, the standard model of the universe is a map that does not yet show the terrain. It captures the outlines of cosmic evolution, but the forces that drive it remain hidden in shadow. The model's precision gives comfort, but that comfort may be temporary. The universe has always rewarded doubt more than certainty. If almost everything the model depends on is invisible, then perhaps the next revolution in cosmology will not come from refining its equations, but from asking whether the darkness itself is a sign that we are missing something more fundamental. Not a new kind of matter, but a new way to understand gravity. The deeper scientists peer into the universe, the clearer it becomes that the standard model of cosmology, while powerful, is not the final description of reality. Its equations describe the motion of galaxies and the evolution of cosmic structure, but they do not explain the underlying cause of those patterns. The lambda-cold dark matter model is a triumph of observation and mathematics, yet its brilliance conceals its fragility. Beneath its success lies a dependence on mysteries it cannot resolve. At its core, the model is built on three great pillars: general relativity, the Big Bang, and the assumption of uniformity. Each has been tested and confirmed, but each also contains limits that point toward a deeper theory waiting to be found. General relativity, despite its precision, breaks down at singularities where space-time curvature becomes infinite. The Big Bang, while supported by abundant evidence, cannot explain what triggered expansion or what existed before it. And the assumption that the universe is the same in every direction may not hold when we examine the largest cosmic structures ever discovered: vast filaments and voids, stretching hundreds of millions of light-years across. When cosmologists simulate the universe within this framework, the results match observation with uncanny accuracy. Yet to make those simulations work, they must insert values, constants, densities, and parameters whose physical origins remain unknown. The cosmological constant, for example, functions as a kind of energy embedded in the vacuum of space. It causes the universe to expand faster over time. But quantum field theory predicts a vacuum energy so enormous that space would tear itself apart in an instant. The observed value is smaller by a factor of 10 to the power of 120, the largest discrepancy in the history of science. It is as though nature has fine-tuned itself with impossible precision. This fine-tuning problem extends beyond the cosmological constant. The density of matter and the rate of cosmic expansion must have been balanced to an extraordinary degree in the early universe. If the expansion had been slightly faster, matter would have dispersed too quickly for galaxies to form. If slower, gravity would have pulled everything back into a premature collapse. The flatness of the universe, its near-zero curvature, also demands that the initial conditions were set within an unimaginably narrow range. Inflation theory was introduced to explain this, but as of now, it remains an elegant conjecture. Despite these unresolved issues, the Standard Model continues to describe the cosmos better than any alternative. Observations of the cosmic microwave background, measured by the Planck satellite, reveal temperature fluctuations so minute that they correspond almost exactly to the density variations required for galaxies to form. These ripples, imprinted when the universe was only a few 100,000 years old, provide a snapshot of the earliest known structure. By analyzing these patterns, scientists have determined the proportions of the universe's components, the 5% of ordinary matter, the 27% of dark matter, and the 68% of dark energy. Every major cosmological observation supports this distribution. Galaxy rotation curves reveal hidden mass that cannot be explained by visible stars. Gravitational lensing, the bending of light by unseen mass, maps vast halos of dark matter surrounding galaxies and clusters. Type Ia supernovae, serving as cosmic distance markers, show that expansion is accelerating. Even the large-scale clustering of galaxies across billions of light-years follows the patterns predicted by a universe dominated by cold, dark matter and dark energy. The consistency of these results gives the lambda cold dark matter model a status almost unrivaled in the history of science. And yet, the more complete the picture becomes, the more unsettling its implications. 95% of the universe is invisible, and our confidence in its existence rests entirely on the behavior of the remaining 5%. The model may therefore describe not the universe as it is, but the universe as it appears from our narrow vantage point. Our measurements are filtered through light, gravity, and time, and each of these is shaped by the very forces we are trying to understand. This paradox sits at the center of cosmology. The same observations that confirm the model also hint at its limits. The cosmic microwave background, though uniform, shows anomalies, subtle asymmetries between hemispheres, unexplained cold spots, and alignments that seem statistically unlikely. These features could be artifacts of measurement, or they could signal physics beyond the Standard Model. Likewise, the Hubble tension, the disagreement between the universe's expansion rate measured nearby and that inferred from the early universe, persists even after every known source of error has been considered. Some cosmologists suspect that new physics, perhaps involving early dark energy or modified gravity, will be required to reconcile these results. The history of science suggests that when equations fit the data but their meaning remains obscure, a deeper revolution is coming. Newton's laws once described planetary motion with exquisite precision, yet their hidden assumptions about absolute space and time gave way to Einstein's relativity. In the same way, the lambda cold dark matter model may be a prelude to a new cosmological framework, one that explains not only how the universe evolves, but why it exists in this form at all. For now, however, it remains our best map of reality. It gives coherence to countless independent measurements, tying together the past, present, and future of the cosmos in a single mathematical fabric. Its beauty lies in its balance, a simple set of equations capable of describing a universe of staggering complexity. But its beauty should not be mistaken for completeness. The model's success does not prove that it is final. It only proves that it is useful. The deeper lesson of the standard model of cosmology is the same one that has guided science for centuries. Every equation that works perfectly is a temporary truth. The cosmos we know today is built upon mysteries that remain unbroken, and each answer leads us closer to another layer of ignorance. The equations match the evidence, yet almost all of the universe remains invisible. Can a model built upon the unseen truly be complete? Perhaps not. But for now, it gives us the most reliable portrait we have of existence itself. If the standard model of the universe rests on the unseen, then the first step toward understanding must be to confront that darkness. What is the hidden matter that holds galaxies together and shapes the cosmic web? It has never been seen, yet its gravity governs the universe. The search for this missing mass begins. For centuries, astronomers believed they could see the universe clearly. The light of stars, the glow of galaxies, the flicker of distant quasars, all seemed to map the cosmos with precision. But in the 20th century, evidence began to reveal a silent contradiction. The visible universe, magnificent as it was, did not weigh enough to explain its own motion. Something unseen, something vast, was holding it all together. The story of dark matter begins not with speculation, but with measurement. In the 1930s, Swiss astronomer Fritz Zwicky studied the Coma cluster, a collection of galaxies bound together by gravity. He compared the speed of the galaxies to the mass that could be inferred from their light. The result was astonishing. The galaxies were moving far too fast to be held together by the visible matter alone. By the rules of gravity, the cluster should have flown apart long ago. Zwicky concluded that some invisible mass, which he called dunkel materie, or dark matter, must be present, exerting a gravitational pull strong enough to keep the cluster intact. At the time, his idea seemed radical. Many astronomers dismissed it as an error in measurement or an oversimplification of galactic dynamics. For decades, dark matter remained a curiosity, an unsolved discrepancy, rather than a crisis. But in the 1970s, the evidence could no longer be ignored. Vera Rubin and Kent Ford, studying the rotation curves of spiral galaxies, found that stars on the outer edges moved just as fast as those near the center. According to Newtonian mechanics, speeds should have decreased with distance, just as planets far from the sun orbit more slowly. Yet the galaxies refused to obey this rule. The simplest explanation was that each galaxy was surrounded by a vast, invisible halo of mass, extending far beyond the visible stars. Rubin's observations transformed dark matter from speculation into necessity. The same pattern appeared everywhere astronomers looked in dwarf galaxies, in massive clusters, and even in the cosmic web that connects them. The luminous matter we see, it turned out, is only the tip of an iceberg, tracing the outlines of something deeper. Without this unseen mass, galaxies would disintegrate and clusters would dissolve. The cosmic structure itself would collapse. The evidence soon expanded beyond rotation curves. Gravitational lensing, the bending of light by gravity, revealed that light from distant galaxies was distorted far more than visible matter alone could account for. One of the most striking examples is the Bullet cluster, two colliding galaxy clusters observed through X-ray and optical telescopes. When scientists mapped the mass distribution using lensing, they found that most of the mass did not coincide with the hot gas seen in X-rays, which contains most of the normal matter. Instead, it followed the galaxies themselves, which passed through each other with little interaction. This separation showed that the dominant component of mass does not collide or slow down. It passes through space almost invisibly. The Bullet cluster became one of the clearest demonstrations that dark matter is real. The behavior of its components, luminous gas, stars, and unseen mass, could not be explained by modified gravity alone. The invisible matter seemed to act like a transparent scaffold, guiding the collision while remaining unaffected by it. Other systems, such as the El Gordo cluster and the Musket Ball cluster, confirm this pattern on cosmic scales. Yet despite this overwhelming indirect evidence, no one has ever detected a single particle of dark matter directly. The search has stretched across decades and continents. Physicists have proposed several candidates, each born from the theories that extend beyond the standard model of particle physics. The most prominent are weakly interacting massive particles, or WIMPs, heavy particles, that interact through gravity and the weak nuclear force, but not with light. For years, massive underground detectors buried beneath mountains and ice sheets have waited for a single WIMP to collide with an atomic nucleus. None have yet appeared. Another possibility is the axion, a lightweight particle proposed to solve a different problem in quantum chromodynamics, the apparent symmetry of the strong nuclear force. Axions could be produced in enormous numbers in the early universe and might make up the dark matter today. Experiments such as ADMX, using ultra-sensitive microwave cavities, have searched for the faint conversion of axions into photons. The search continues, but so far, no signal has been found. Sterile neutrinos represent another intriguing idea. Ordinary neutrinos, nearly massless particles that stream through matter by the trillions each second, are known to exist in three types. A hypothetical fourth kind, the sterile neutrino, would interact only through gravity. If it exists, it could contribute to the universe's missing mass. Observations of X-ray emissions and cosmic structure formation have offered hints, but no confirmation. As each new experiment refines its sensitivity, the parameter space for these candidates shrinks. The longer the silence continues, the more uneasy physicists become. Some have begun to question whether dark matter is truly a particle at all. Alternative theories have emerged that challenge the very framework of gravity. Modified Newtonian dynamics, or MOND, proposed by Mordechai Milgrom in the 1980s, suggests that the laws of motion change at extremely low accelerations, such as those found in the outskirts of galaxies. According to MOND, the flat rotation curves could be explained without invoking unseen matter. While MOND reproduces galactic behavior well, it struggles to explain gravitational lensing and the dynamics of galaxy clusters. Relativistic extensions of MOND, such as tensor, vector, scalar gravity, attempt to reconcile these problems within Einstein's framework, but none have achieved universal acceptance. The failure to detect dark matter particles directly does not invalidate the concept. It only deepens the mystery. Observations from the cosmic microwave background, large-scale structure formation, and gravitational lensing all converge on the same conclusion. Whatever dark matter is, it exists, and it shapes the universe's evolution. It is the invisible architect of the cosmic web, the silent foundation on which galaxies rise. Still, the question remains unanswered. What is it made of? It exerts gravity, but emits no light. It clusters yet does not collide. It dominates the mass of the universe, but refuses to reveal itself. This is not ignorance born of speculation. It is ignorance defined by precision. The data are clear, and the explanation eludes us. If dark matter remains invisible after half a century of searching, are we missing the matter or misunderstanding gravity itself? The answer may determine the next great revolution in physics. The idea that most of the universe is made of something invisible seems impossible, yet every line of evidence points toward it. The motions of galaxies, the bending of light, the growth of structure all behave as if an unseen mass pervades the cosmos. Still, after decades of searching, dark matter has remained entirely silent. The more precise our instruments become, the deeper the silence grows. It is as if the universe hides its scaffolding behind a veil that no particle detector can lift. The quest to uncover dark matter has driven some of the most ambitious experiments in the history of science. Deep underground, beneath kilometers of rock and ice, detectors sit in perfect darkness, shielded from cosmic rays and radiation. They wait for an event so rare that it may happen only once in a year, a single collision between a dark matter particle and an atomic nucleus. Liquid xenon tanks, cryogenic crystals, and supercooled detectors all share the same hope: that one day, a faint flash of light or a tiny vibration will confirm that dark matter has touched the visible world. So far, those flashes have not come. Each experiment, from the Large Underground Xenon Detector to Panda X and Super CDMS, has reported no conclusive detection. Occasionally, a signal appears to hint at success, but repeated tests erase the hope. The search is not failure, it is calibration. Every null result narrows the possibilities, tightening the constraints on what dark matter could be. But as each candidate is ruled out, a deeper question emerges. What if the thing we are looking for does not exist in the form we expect? Astronomers have also looked beyond Earth for clues. The distribution of dark matter can be traced indirectly through the way galaxies cluster and how light from distant objects bends around them. Weak gravitational lensing, observed by telescopes such as the Hubble Space Telescope and the Vera-C, Rubin Observatory, reveals vast halos of unseen mass surrounding galaxies and linking them in filaments that span cosmic distances. Simulations of the early universe, based on the lambda-cold dark matter model, reproduce these patterns almost exactly. The large-scale cosmic web appears to require dark matter to exist. Without it, the universe would look nothing like what we see. The case for dark matter, therefore, does not rest on a single observation. It is a network of evidence drawn from multiple domains of physics and astronomy. The cosmic microwave background, mapped by the Planck satellite, shows minute temperature fluctuations that correspond to regions of higher and lower density in the early universe. The patterns in that radiation can only be explained if an unseen form of matter helped gravity shape structure before atoms or stars existed. The same pattern emerges in the way galaxies formed over billions of years. They seem to grow around invisible frameworks that attract ordinary matter like dust collecting on a spider's web. Yet the precise nature of this framework remains elusive. The favored explanation, cold, dark matter, assumes that the unseen particles move slowly compared to the speed of light and interact only through gravity. This produces the right kind of structure on large scales. But on smaller scales, within galaxies and clusters, discrepancies begin to appear. Simulations of cold, dark matter predict dense centers and countless small satellite galaxies that are not observed. Some physicists have proposed warm dark matter, composed of lighter, faster particles that smooth out these small-scale clumps. Others suggest self-interacting dark matter, whose particles occasionally collide with one another, redistributing energy and softening dense regions. Each of these refinements keeps the concept alive, but none solve it completely. Meanwhile, alternative approaches attempt to remove the need for dark matter altogether. Modified Newtonian dynamics adjusts the laws of motion so that gravity becomes stronger at very low accelerations, matching galactic rotation curves without invisible mass. More sophisticated theories such as modified gravity, scalar, tensor, vector gravity, and emergent gravity try to incorporate these effects within Einstein's framework. However, none of these models explain all observations at once, especially the bullet cluster and the cosmic microwave background, both of which fit naturally under the dark matter hypothesis. The impasse leaves cosmology at a crossroads. On one side lies a universe filled with invisible matter that accounts for most of its mass. On the other lies the possibility that gravity itself behaves differently than we imagine. Both possibilities are profound. To confirm dark matter as a new form of matter would expand the known inventory of the universe beyond imagination. To discover that gravity is incomplete would require rewriting one of the most successful theories in history. For now, evidence favors the existence of dark matter, though its nature remains an open wound in physics. Every experiment that fails to find it deepens the mystery, but also strengthens the discipline of inquiry. The absence of confirmation has forced cosmologists to reconsider their assumptions, refine their models, and design ever more sensitive instruments. This relentless pursuit mirrors the very foundation of science, progress through the correction of error. What makes dark matter so haunting is not just that we cannot see it, but that we can feel its presence in every observation. It binds galaxies, sculpts the cosmic web, and anchors the universe's architecture, yet it hides in plain sight. Its gravitational fingerprint is everywhere, but its physical identity is nowhere to be found. The cosmos whispers its name in the motions of stars and the warping of light, but no laboratory has yet caught its voice. The mystery of dark matter reminds us that knowledge often begins with what cannot be seen. Just as Copernicus displaced Earth from the center of the universe, and Einstein displaced time from its absolutes, the search for dark matter displaces our confidence in visibility itself. The universe does not owe us transparency. It allows us glimpses of its structure, but it keeps its substance veiled. The question grows sharper with every passing year. Is dark matter a real material, or a sign that gravity behaves differently than we thought? Each possibility carries the promise of a new revolution. Whether the answer lies in undiscovered particles or in a reformulation of spacetime, it will reshape our understanding of what the universe truly is. The silence of dark matter is not emptiness, it is the sound of a question still being asked. The search for dark matter has become one of the defining quests of modern physics, not only because of what it might reveal, but because of what it forces us to confront about our methods of knowing. For decades, scientists have tried to bring the unseen into the realm of the measurable, but the universe continues to guard its secret. The further we reach into the darkness, the more it feels as though we are tracing the outline of a shadow with instruments made of light. Even without direct detection, the effects of dark matter are undeniable. Galaxies rotate, lensing bends light, and structure grows according to its presence. Yet it has no color, no charge, and no interaction with electromagnetic forces. It cannot be seen or touched, yet it defines the shape of everything that can be. In a universe governed by visibility, dark matter has rewritten the meaning of evidence. It is not something we see, but something we infer, an invisible cause, revealed by visible consequences. This shift in understanding reflects the maturity of modern science. The recognition that something unseen can be as real as the things we observe marks a departure from the older, simpler universe of Newton and Galileo. It is no longer enough to describe what the eye can perceive. The universe operates on scales and principles that transcend human intuition. The unseen is not mystical. It is measurable through its influence. Science, in this sense, has become the art of detecting the invisible. Yet for all its rigor, the pursuit of dark matter also exposes the limits of our tools. The detectors buried beneath mountains are built on assumptions drawn from known physics assumptions about how particles should behave, how forces should interact, and how probability should distribute energy. If dark matter belongs to a realm of physics we have not yet discovered, then our detectors may simply not be tuned to its frequency. We might be listening for a whisper in the wrong language. Some scientists have begun to explore this possibility through ideas that stretch beyond traditional physics. Perhaps dark matter is not a single particle but an entire hidden sector, a shadow universe that interacts with ours only through gravity. In this view, dark matter could form its own structures, its own dark atoms and dark galaxies, invisible to us but gravitationally intertwined with our own. Others have suggested that dark matter may arise from the collective behavior of space-time itself, an emergent property, rather than a separate ingredient. These ideas remain speculative, but they reveal the growing recognition that the mystery may demand a new kind of thinking, one that blurs the line between matter and geometry. Whatever its nature, dark matter has already changed the way we understand existence. It has shifted the focus of cosmology from what we can see to what we can deduce. The universe has become a landscape of inference, where light traces only the contours of deeper, hidden forms. This recognition humbles our place in the cosmos. For centuries, we believed that seeing was understanding. Now we know that the majority of reality lies beyond light itself. Dark matter also redefines our sense of connection to the universe. It surrounds every galaxy, including our own Milky Way, forming a vast halo that stretches far beyond the visible disk of stars. The Earth moves through this invisible sea, and at any given moment, billions of dark matter particles may pass through our bodies unnoticed. We live within a cosmic architecture that is almost entirely unseen, held together by a gravitational field that neither reflects nor absorbs light. To grasp this is to realize that existence is not built solely from the visible, but from the interplay between what is seen and what is hidden. Despite the frustration of decades without direct detection, scientists remain undeterred. The story of discovery has always been one of persistence against uncertainty. The same patience that once revealed the structure of atoms and the curvature of space-time now drives the search for dark matter. New experiments, such as the Lux Zeppelin detector and space-based observatories, continue to push the boundaries of sensitivity. The upcoming generation of particle accelerators and cosmic surveys may yet glimpse the faint signature of the invisible. But even if the day comes when we identify dark matter's true form, it will not mark the end of the story, only the beginning of a new one. Each answer in science reveals a deeper layer of ignorance. Discovering dark matter will not close the book on cosmology. It will open a new chapter on the nature of mass, gravity, and the structure of the universe itself. For now, the missing mass remains a reminder of humility. The cosmos is not obligated to reveal its secrets quickly. It teaches through absence as much as through evidence. What we cannot see still governs what we can, and every unanswered question becomes a bridge to the next discovery. If dark matter continues to evade detection, we may need to reconsider our assumptions once more. Perhaps gravity behaves differently on cosmic scales, or perhaps space-time itself carries a hidden complexity that mimics the presence of unseen mass. Whatever the outcome, the search ensures that science remains what it has always been, a discipline defined not by certainty, but by the courage to confront the unknown. The universe's silence about its missing mass is not a refusal to speak. It is an invitation to listen more deeply. The next revelation may not come from seeing something new, but from realizing that what we thought we understood about space, time, and matter has been incomplete all along. If dark matter remains invisible after half a century of searching, are we missing the matter or misunderstanding gravity itself? That question now stands at the frontier of cosmology, waiting for the next observer, the next experiment, the next moment when being wrong leads us closer to the truth. Yet dark matter is only half of the universe's hidden story. If unseen mass holds the cosmos together, an even more mysterious force tears it apart. In the late 20th century, astronomers discovered that the expansion of the universe is accelerating, driven by an unknown energy that fills space itself. This is the other great enigma, the force we cannot explain. For most of the 20th century, scientists assumed that the universe's expansion, first observed by Edwin Hubble, would gradually slow down under the pull of gravity. Every galaxy, every cluster, every particle of matter, visible or dark, exerts a gravitational tug on every other. The cosmos might expand forever, or it might one day collapse in a big crunch, but the rate of expansion was expected to decrease over time. Then, in the final years of that century, the universe defied all expectations. In 1998, two independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, set out to measure the deceleration of the universe's expansion. They used Type Ia supernovae, powerful stellar explosions that shine with nearly uniform brightness, as cosmic distance markers. By comparing their apparent brightness with their redshift, astronomers could determine how quickly the universe was expanding at different points in its history. The result was shocking. The distant supernovae were dimmer than predicted, not because they were farther away in a slowing universe, but because the expansion of space had accelerated. It was as though an unseen force was pushing galaxies apart, overwhelming gravity on the largest scales. The discovery was one of the most profound in modern cosmology. The universe was not slowing down, it was speeding up. The simplest explanation, consistent with Einstein's equations, was the revival of a term he had once introduced and later abandoned: the cosmological constant. This constant represented a form of energy intrinsic to space itself, a pressure that does not dilute as the universe expands. Today, that energy is called dark energy. Dark energy is not a new particle or field in the traditional sense. It is a property of spacetime. According to general relativity, energy and mass are equivalent, and both curve the fabric of the cosmos. If space contains an inherent energy, then that energy exerts a gravitational effect, but unlike ordinary gravity, it acts repulsively. Instead of pulling objects together, it drives them apart. The cosmological constant, represented by the Greek letter lambda, embodies this idea. When inserted into Einstein's field equations, it produces an expansion that accelerates with time. This simple term fits the observations beautifully. When combined with cold dark matter and normal matter, the lambda cold dark matter model reproduces the cosmic microwave background, the distribution of galaxies, and the accelerating expansion seen in supernova data. It explains why distant galaxies move away faster than nearby ones, why the universe's geometry appears flat, and why structure formation slowed after a certain epoch. Yet the elegance of this explanation hides one of the most troubling problems in physics: the vacuum, energy, catastrophe. According to quantum field theory, empty space is not truly empty. It seethes with fluctuations, pairs of virtual particles that constantly appear and disappear. Each of these fluctuations contributes a tiny amount of energy to the vacuum. When physicists sum over all possible fluctuations, the predicted energy density of the vacuum is enormous, roughly 10 to the power of 120 times greater than the value inferred from cosmic acceleration. The observed cosmological constant is so small compared to this theoretical prediction that the discrepancy is sometimes called the worst calculation in the history of physics. This mismatch reveals a fundamental conflict between quantum theory and general relativity. Quantum field theory describes energy at the smallest scales, while general relativity governs the curvature of space-time. Both are extraordinarily successful in their respective domains, yet when applied together, they produce nonsense. Somehow, the energy of the vacuum must gravitate far less than expected, or there must be an unknown mechanism that cancels almost all of it. But what that mechanism is remains a mystery. Other possibilities have been proposed. Perhaps dark energy is not constant, but dynamic, an evolving field that changes over time. This idea, known as quintessence, suggests that dark energy could behave differently in the past and future, altering the fate of the universe. Quintessence would act like a fluid with negative pressure, its density decreasing more slowly than that of matter as the universe expands. Observations so far have not required such a modification, but they cannot rule it out either. Still, other theories go further, suggesting that the observed acceleration might not be caused by a new form of energy at all, but by a breakdown of general relativity on cosmic scales. Modified gravity theories attempt to reproduce the effects of dark energy by altering Einstein's equations, changing how space-time responds to mass and energy over vast distances. Some of these models involve additional dimensions, scalar fields, or geometric corrections, but none have yet provided a clear or unique explanation that matches all observations as well as the cosmological constant does. What makes dark energy so strange is its scale. Unlike dark matter, which dominates galaxies and clusters, dark energy operates everywhere equally, even in the emptiest voids. It is not localized or concentrated, it fills space uniformly. As the universe expands, more space is created, and with it, more dark energy. This means that while the density of matter decreases over time, the density of dark energy remains constant. Eventually, as matter and radiation grow ever more dilute, dark energy will dominate completely. Cosmologists can already glimpse this future in the equations. If the cosmological constant remains constant, the universe will continue to expand forever, with galaxies drifting beyond each other's horizons. Stars will burn out, galaxies will fade, and the night sky will grow dark as the observable universe becomes smaller and emptier to any observer that remains. It is a vision not of collapse, but of isolation, a cosmos that ends, not in fire, but in fading. And yet, even this fate depends on an assumption we do not truly understand. We know that dark energy exists because of what the data demands, not because of what we can see. Its effect is subtle but decisive, an invisible pressure embedded in the structure of reality. If it were slightly weaker, galaxies might have formed earlier and larger. If slightly stronger, matter might never have coalesced at all. The fact that the universe exists in its present form suggests an improbable balance. The discovery of dark energy has forced scientists to confront the possibility that the universe may be far stranger than even Einstein imagined. The same equations that describe the curvature of space-time may be hinting at something deeper, perhaps that space and time themselves are emergent properties of a more fundamental layer of physics. If that is true, dark energy may not be a substance or a field, but a sign that our understanding of space-time is incomplete. For now, however, dark energy remains a placeholder for ignorance, a symbol of humility in the face of cosmic complexity. We can measure its effect, calculate its contribution, and include it in our equations, but we cannot yet explain what it is. It is the quiet engine of the universe's acceleration, a force we can neither touch nor contain, yet one that will determine the ultimate fate of everything. The discovery of dark energy changed not only cosmology, but the very way scientists think about reality. It forced a recognition that the largest structures of the universe are driven by a phenomenon that no one has ever detected directly. Even the most sophisticated instruments cannot isolate it, yet its influence shapes the entire evolution of the cosmos. In the history of science, few discoveries have been so deeply unsettling. For the first time, physicists faced the possibility that the fate of everything is controlled by something entirely invisible, woven into the fabric of space itself. In the years after 1998, astronomers confirmed the presence of dark energy through multiple lines of evidence. Observations of the cosmic microwave background revealed patterns in the primordial radiation that could only arise in an accelerating universe. Measurements of baryon acoustic oscillations, faint ripples in the distribution of galaxies caused by sound waves in the early universe, gave the same result. Even the way clusters of galaxies evolve and the rate at which new structures form point to an expanding space that accelerates over time. The evidence became overwhelming. Dark energy dominates the cosmic energy budget, accounting for roughly 2/3 of all the energy in existence. But dominance does not mean understanding. Every attempt to explain dark energy leads to contradictions or unanswered questions. If it is the cosmological constant, why does its value differ from quantum predictions by a factor of 10 to the power of 120? If it is a dynamic field like quintessence, why has it remained so uniform and stable across billions of years? If it represents a flaw in general relativity, why does the rest of relativity's framework continue to match every other observation so perfectly? The more precisely dark energy is measured, the more it seems to sit at the intersection of all our unsolved theories. The simplest explanation remains the cosmological constant, a constant energy density filling space. In this view, as space expands, new regions of vacuum appear, each with the same energy density. The total energy of the universe therefore increases over time, driving further acceleration. The mathematics works, and the observations fit, but the conceptual puzzle remains unsolved. Why does empty space have energy at all? In physics, energy usually arises from fields, forces, or matter. Yet dark energy appears to be none of these. It is not generated or consumed, not exchanged or transformed. It simply exists. For some physicists, this apparent strangeness hints at a deeper truth. The energy of the vacuum might not be a property of particles or fields, but of spacetime itself. In the quantum view, spacetime is not a smooth continuum, but a fluctuating sea of virtual events. The cosmological constant could be the residual effect of those fluctuations, averaged over enormous scales. But even this interpretation does not solve the problem of magnitude. Why is the effect so small compared to what theory predicts? Some have proposed that the answer lies in the nature of the multiverse, that our universe is just one of many, each with a different value of the cosmological constant, and that only in those where the value is small enough can galaxies and observers exist. While this reasoning might explain the coincidence, it drifts toward the edge of what can be tested, and therefore toward the edge of science itself. Others seek more tangible solutions through new physics. In models of quintessence, a scalar field slowly rolls toward a minimum of potential energy, providing a time-varying pressure that drives cosmic acceleration. These models predict subtle differences in how the rate of expansion changes over time, and future surveys such as Euclid and the Vera-Rubin Observatory are designed to detect them. If such variations are found, they could reveal that dark energy is not constant after all, but a living field, evolving across cosmic history. Yet even this would raise another question: what gives rise to the field, and why does it act on space so uniformly? More radical theories modify gravity itself. Perhaps the equations of general relativity, though accurate within the solar system, break down on scales of billions of light years. Extensions such as F, R, gravity, massive gravity, or extra-dimensional models attempt to reproduce the observed acceleration without introducing a new form of energy. These frameworks can mimic the effects of dark energy, but they also introduce complexities that often conflict with precision tests of gravity. The challenge is to alter the laws of the universe without undoing the accuracy of everything they already explain. The struggle to understand dark energy is not merely a technical issue, it is philosophical. It challenges the assumption that the universe is comprehensible through known forces and particles. It reminds scientists that every model, no matter how precise, is built upon human interpretation of observation. When Einstein introduced the cosmological constant, he did so to preserve a static universe, an idea soon overturned by Hubble's discovery of expansion. Decades later, the same term returned to describe an accelerating universe. The constant never changed, only our understanding of what it meant. In the current era, dark energy stands as both a triumph and a riddle. It shows that human curiosity can uncover phenomena beyond imagination, yet it also exposes how much remains hidden. Our telescopes see the faintest galaxies from billions of years ago, but they cannot see the force that shapes their motion. Our equations describe the curvature of space-time, but they cannot reveal why space itself expands. The mystery is not one of ignorance, but of the limits of observation. Perhaps this limit is not permanent. As technology advances, new ways of measuring the universe may reveal hints about the nature of dark energy. Gravitational wave detectors could probe the cosmic expansion in new ways. Surveys of large-scale structure could expose deviations from uniformity that betray the behavior of an evolving field. The coming decades will bring data of unprecedented precision, and with it, the possibility that the veil may lift even slightly. But even if we find the mechanism, the lesson remains the same. Every solution in science opens another question. The discovery of dark energy, like that of dark matter, is a reminder that the universe does not yield its truths easily. What we call understanding is often only a temporary balance between knowledge and mystery. Dark energy compels us to face the unknown not as an exception, but as the norm. It teaches that the universe is governed not only by what we can detect, but by forces beyond our direct reach. The more deeply we study the cosmos, the more it seems that invisibility is its most fundamental trait. Dark energy forces us to confront a possibility that science has long resisted, that the ultimate laws of the universe may not be intuitive, and that the very concept of emptiness is an illusion. For centuries, vacuum was imagined as nothingness, a background stage upon which matter and energy played their roles. Now we know that the vacuum itself is active, restless, and filled with potential. Space is not an empty container. It is a participant in the cosmic drama. Dark energy is its most mysterious act. In the modern view, space expands not because something pushes it outward, but because the geometry of spacetime evolves according to its energy content. The cosmological constant, that tiny term reintroduced into Einstein's equations, does not drive expansion like a physical explosion. Instead, it alters the relationship between space, time, and gravity, so that distances between galaxies grow even without motion through space. This expansion does not carry galaxies through a medium. It stretches the medium itself. Every cubic centimeter of space, no matter how empty, contains a minuscule amount of energy that collectively shapes the universe's destiny. The presence of this energy means that the fate of the cosmos is already written in its equations. If the cosmological constant remains constant, expansion will continue forever, and the universe will move toward a state known as the cosmic heat death. Over unimaginable timescales, galaxies will drift beyond each other's horizons, their light stretched into wavelengths too long to be seen. Stars will exhaust their fuel, planets will freeze, and black holes will evaporate through quantum radiation. The universe will become a thin mist of particles, and radiation spread across an ever-growing void. In that distant epoch, dark energy will be the only remaining force, silently separating everything from everything else. Some scientists have speculated about other possibilities. If dark energy changes with time, the universe could face very different futures. A weakening dark energy might allow gravity to reassert itself, eventually halting expansion and triggering collapse. A strengthening one could lead to a big rip, where galaxies, stars, and even atoms are torn apart as the expansion accelerates without limit. Observations so far suggest that dark energy remains constant, but the truth may lie hidden in subtle variations that only future instruments can detect. These vast scenarios, though beyond human timescales, matter deeply to our understanding of physics. They tell us that the ultimate fate of the cosmos depends not on matter or radiation, but on the geometry of space itself. In the end, the universe's destiny is written in the properties of nothingness. This realization collapses the old divide between something and nothing. What we once called empty space turns out to be the most powerful component of existence, an ocean of energy, shaping time, gravity, and expansion. The mystery of dark energy has also reignited a deeper question. Why is the universe understandable at all? Our equations, however incomplete, continue to describe phenomena that extend billions of light years beyond human experience. They work across extremes of scale and time that no experiment can directly reach. And yet, those same equations conceal profound inconsistencies. Quantum field theory and general relativity, the two greatest triumphs of physics, cannot coexist peacefully when applied to the vacuum. One predicts infinite energy, the other demands balance. Their conflict at the heart of dark energy suggests that our most trusted frameworks are fragments of a larger, undiscovered whole. Perhaps that is the greatest message of dark energy, that even our most successful models are temporary. The universe has always humbled its observers. The Earth was not the center, light was not infinite, time was not absolute, and now emptiness is not empty. Each revelation dismantles an illusion and replaces it with something stranger, something less human and more vast. Dark energy stands as the latest reminder that understanding is not possession. We do not own the universe's truths. We approach them asymptotically, through observation and doubt. In the laboratories and observatories of the world, the search continues. astronomers mapped the sky with unprecedented detail, tracing how galaxies cluster and how light stretches across billions of years. Physicists refine their models of the quantum vacuum, searching for hints of the mechanism that makes nothingness act like something. Mathematicians explore new geometries and symmetries that might reconcile the contradictions between gravity and quantum theory. Each discipline circles the same enigma, a universe whose largest structures and ultimate fate depend on a form of energy that no one can explain. Dark energy reminds us that the unknown is not a failure of science, but its heartbeat. It is the reason inquiry persists, the force that drives curiosity forward. The discovery that the universe is accelerating did not end cosmology. It opened a new frontier, one where physics, philosophy, and observation converge. The challenge now is not merely to measure the cosmos, but to redefine what we mean by understanding itself. If the universe's expansion is driven by something we cannot detect, is dark energy real or simply a sign that our theories are incomplete? The answer remains suspended between observation and imagination. But history suggests that when we stand at such crossroads, the next revolution is already beginning. The discovery of dark matter and dark energy has rewritten our sense of reality, yet both arise from a deeper question: how did it all begin? The story of the universe's origin, from the first fraction of a second to the galaxies we see today, is still incomplete. The Big Bang remains our best explanation, but even it begins with equations that break down at the very start. To understand the limits of our knowledge, we must return to the moment where everything began, and to the boundaries where our understanding ends. Every story of the universe begins with the same question: how did it all begin? For centuries, philosophers and theologians speculated about creation, but only in the 20th century did science discover that the universe had an origin that could be measured. The evidence is written across the sky in the faint radiation that fills space, in the motions of galaxies, and in the abundance of the lightest elements. All point to a moment when everything, space, time, energy, and matter, emerged from a single, unimaginably hot and dense state. We call this beginning the Big Bang. The idea was not immediately accepted. In the early 20th century, Einstein's general relativity introduced a dynamic universe, one that could expand or contract. But even Einstein found this conclusion unsettling. He added the cosmological constant to his equations to keep the universe static, believing the cosmos eternal and unchanging. When Edwin Hubble, in 1929, showed that galaxies were receding from one another, the evidence became impossible to ignore. Space itself was expanding. Run that expansion backward, and all of matter and energy converge to a single origin. The concept of a cosmic beginning was radical. It implied that the universe had not always existed, that it had a finite age. In the 1940s, Belgian physicist Georges Lemaitre, who was also a priest, proposed that the universe began as a primeval atom, an initial state that exploded outward. Others, including George Gamow and Ralph Alpher, developed the theory further, predicting that the early universe would have been dense enough for nuclear reactions to occur, forming the first light elements. If that were true, the universe should be filled with leftover radiation, the afterglow of creation. That afterglow was found by accident. In 1965, Arno Penzias and Robert Wilson, working at Bell Labs, detected a faint, persistent hiss of microwave radiation that seemed to come from every direction. It was not interference, not an artifact of their instruments. It was the cosmic microwave background, the fossil light of the universe's infancy. This discovery provided the first decisive proof that the universe had indeed begun from a hot, dense state. The Big Bang was no longer a theory of faith. It was a theory of measurement. Over time, more evidence accumulated. The relative abundances of hydrogen, helium, and lithium matched predictions from Big Bang nucleosynthesis. The large-scale distribution of galaxies reflected the small fluctuations imprinted on the early universe, now visible in the cosmic microwave background as minute temperature variations. Each observation confirmed that the cosmos evolved from an initial fireball to the complex structure we see today. Yet for all its success, the Big Bang theory does not describe the actual beginning. It describes what happened after the universe became large and cool enough for known physics to apply. When we trace the equations of general relativity backward, we eventually reach a singularity, a point where density and temperature become infinite and the laws of physics cease to function. At that boundary, general relativity can no longer describe space or time. It is not a true beginning, but a limit of understanding. The singularity is not an object in space. It is the point where the very concepts of space and time lose meaning. The Big Bang, therefore, is not an explosion in space. It is the expansion of space itself. Every point in the universe was once compressed into that early state, and the expansion continues everywhere equally. There is no center from which it expands, and no edge to which it expands. What we call before the Big Bang may not even be a meaningful question within our current framework. Time itself began when the universe began. Asking what happened before time started is like asking what lies north of the North Pole. Still, scientists have tried to peer beyond that horizon. The first fraction of a second after the Big Bang, a period known as the Planck era, remains shrouded in mystery. In that instant, the universe was smaller than an atom and hotter than anything we can imagine. Gravity was as strong as the other forces, and quantum effects dominated the geometry of space-time. Our known laws cannot describe such a regime. The merging of quantum mechanics and general relativity, a complete theory of quantum gravity, would be required to understand what truly happened. Some clues may lie in cosmic inflation, a theory proposed in the 1980s by Alan Guth, Andre Linde, and others. Inflation suggests that the universe underwent a brief but staggering burst of exponential expansion, growing from subatomic to macroscopic scales in a tiny fraction of a second. This rapid expansion would explain several puzzles that the original Big Bang model could not. It would account for the universe's large-scale uniformity, known as the horizon problem, and its near-perfect flatness, known as the flatness problem. Inflation also provides a mechanism for generating the small quantum fluctuations that later grew into galaxies and clusters. The evidence for inflation is circumstantial but persuasive. The pattern of fluctuations in the cosmic microwave background matches what inflation predicts, a nearly scale, invariant distribution of density variations. Yet direct proof, such as the detection of primordial gravitational waves produced during inflation, remains elusive. Experiments like BICEP and the Planck satellite have searched for these signals in the polarization of the cosmic microwave background, but so far, no definitive trace has been found. Inflation remains a powerful idea awaiting experimental confirmation. Even if inflation occurred, it raises further questions. What caused it? What field drove it? How did it stop? In some versions of the theory, inflation may be eternal, producing a multiverse in which countless universes expand within their own regions of spacetime. These ideas, though mathematically consistent, push beyond what can currently be tested. They represent the edge where cosmology meets philosophy, where the observable ends and speculation begins. What science can say with confidence is that the universe we see today bears the imprint of an extraordinary past. Every galaxy, every atom, every element heavier than hydrogen was forged in processes set in motion by that primordial expansion. The Big Bang is not merely an event long ago, it is an ongoing condition. We live in its aftermath, our existence a continuation of its unfolding. Still, at the limits of the theory, the same pattern reappears, a boundary where understanding breaks down. Just as Newton's laws gave way to relativity, and relativity struggles at the singularity, our current physics reaches its edge at the beginning of time. The Big Bang may not be the absolute start of the universe, but a transition from a prior state, one we cannot yet describe. Whether that state was a quantum fluctuation, a bounce from a previous universe, or something entirely beyond our concepts, remains unknown. The more precisely we study the cosmos, the more we realize that every answer reveals a deeper frontier. The Big Bang is the most successful scientific story ever told about the origin of everything, but it begins with equations that no longer work when pushed to their limit. The universe offers no final beginning, only a chain of origins receding beyond comprehension. To move forward, science must question even the birth of time itself. The Big Bang theory gives us a remarkable view of cosmic history, but its success also exposes its limitations. It tells us what happened after the universe was already expanding, but not why it began to expand. It describes the formation of matter, but not where that matter came from. It explains the evolution of space, but not what space is. The boundaries of the Big Bang are not edges of the universe, they are the edges of knowledge itself. The deeper cosmologists look, the more questions arise about the earliest moments. What triggered the expansion? Was there a before? Could the Big Bang be one phase in a cycle of cosmic rebirths? Or did time itself emerge with that event? These questions reach beyond the realm of observation into the frontier where mathematics and philosophy intertwine. And yet, science continues to push closer to those first instants, using both theoretical insight and experimental observation to narrow the possibilities. During the first second after the Big Bang, the universe changed at a breathtaking pace. In the first 10 to the power of minus 43 seconds, the Planck time, all four fundamental forces may have been unified. After that, gravity separated, followed by the strong nuclear force, and finally the electromagnetic and weak nuclear forces. As the universe expanded and cooled, symmetry broke into complexity. Matter began to dominate over antimatter through processes still not fully understood, leaving behind the material content of the cosmos. These early transitions hint at a deeper structure beneath the known laws of physics. The symmetry breaking that shaped the universe's forces suggests that the universe may have originated from a simpler, higher dimensional, or unified state. Grand unified theories, and more ambitiously, string theory, attempt to describe this early unity. In string theory, the building blocks of nature are not point particles, but tiny vibrating strings whose modes determine the properties of particles. Space itself may contain extra dimensions, compactified so tightly that we do not perceive them. In such frameworks, the Big Bang could represent not a beginning, but a transition, the unfolding of a higher dimensional geometry into the space-time we inhabit. Loop quantum gravity, another approach to quantum cosmology, offers a different insight. It attempts to quantize space-time itself, suggesting that space is made of discrete loops rather than a smooth continuum. In this picture, the singularity at the Big Bang is replaced by a bounce. As the universe contracts to extreme density, quantum effects cause it to rebound, giving birth to expansion. The Big Bounce model removes the need for an infinite beginning and replaces it with a cyclic pattern, universes collapsing and re-emerging endlessly. These theories remain speculative, but they share a common message. The singularity is not the end of explanation, but a doorway to new physics. Evidence for what came before the earliest observable moment is difficult to obtain, yet scientists continue to search for traces of it in the cosmic microwave background. Minute patterns of polarization, subtle temperature anisotropies, or non-Gaussian fluctuations could hold clues to physics beyond the Big Bang. The upcoming generation of telescopes, both ground-based and orbital, aim to measure these features with unprecedented precision. If hints of primordial gravitational waves or other signatures are found, they could reveal what the universe was doing before it became transparent to light. Even as researchers look backward in time, the concept of the Big Bang itself continues to evolve. The term Big Bang can be misleading. It evokes an image of an explosion in empty space, but in reality, it describes the uniform stretching of space, everywhere, at once. Every observer, no matter where they are, sees the rest of the universe receding in all directions. The expansion is not from a center, but of the fabric itself. If one could travel backward in time, one would not approach a point in space, but a state of increasing density and temperature. The question of where the Big Bang happened is meaningless. It happened everywhere. The boundaries of the theory also include conceptual ones. The horizon problem, for instance, asks how regions of the universe that were never in contact could have the same temperature. The cosmic microwave background is astonishingly uniform, differing by only a few parts in 100,000 across the sky. Inflation provides an elegant solution, suggesting that all regions were once close enough to share thermal equilibrium before being stretched apart. Yet without direct evidence, inflation remains a hypothesis, albeit one strongly supported by observation. Another challenge is the flatness problem. Observations show that the geometry of the universe is nearly flat, meaning that parallel lines remain parallel over cosmic distances. Without fine-tuning, any slight curvature in the early universe would have grown dramatically over time, leading to either a rapid collapse or a runaway expansion. Inflation again offers an explanation. By expanding space by an enormous factor, it smooths out any initial curvature. But if inflation occurred, what mechanism started it and stopped it? That remains unknown. The Big Bang model thus sits on a paradoxical foundation. It is both the most successful and the most incomplete description of reality. It explains the universe's evolution from a fraction of a second onward with astonishing accuracy, yet it begins with a failure, a point where physics itself breaks down. The closer we approach the beginning, the more our mathematics dissolves into uncertainty. This realization has philosophical as well as scientific weight. If the laws of physics cannot describe the origin of those very laws, then perhaps there is a fundamental boundary to what science can know. It may not be a limit of intelligence or technology, but a structural limit built into reality. The beginning of time might not be observable because observation itself is a process that requires time. The origin may forever remain hidden behind the horizon of existence, accessible only through inference and imagination. Yet the pursuit continues. The search for a theory of quantum gravity, one that unites general relativity and quantum mechanics, is not merely an academic exercise. It is an attempt to bridge the greatest divide in modern science. Without such a theory, our picture of the universe will always be divided. One law for the large and another for the small, two halves of a whole that refuse to meet. The Big Bang is where those two laws collide. At the boundaries of knowledge, humility becomes the most important tool. The universe has always been larger, stranger, and more self-consistent than our models suggest. The Big Bang theory, for all its power, is likely another approximation, an extraordinary one, but still incomplete. To go beyond it, we must be willing to question the origin of time itself and accept that even the act of questioning is bound by the very fabric we are trying to understand. In the modern age of cosmology, the Big Bang stands as both a cornerstone and a question mark. It anchors our understanding of the universe, yet it invites us to question the assumptions upon which that understanding rests. Every telescope, every particle collider, every satellite that peers into the deep past adds precision to its outline, but none can reveal the moment before. The closer science approaches the beginning, the more that beginning dissolves into mystery. When we look at the oldest light in the cosmos, the cosmic microwave background, we are seeing the universe as it was roughly 380,000 years after the Big Bang. Before that time, the universe was opaque. Matter and radiation were so tightly coupled that photons could not travel freely. Beyond that luminous curtain, direct observation becomes impossible. The earliest moments must be reconstructed through theory and inference, using the traces left behind in temperature variations, particle abundances, and gravitational patterns. This is what makes cosmology both precise and poetic. It is a science built on evidence, yet it deals with events that can never be seen directly. The data are solid: the redshift of galaxies, the background radiation, the ratios of light elements, and they converge on a single narrative. The universe expanded from a hotter, denser state and has been cooling ever since. But this narrative, as solid as it seems, is still a framework drawn upon the fog of the unknown. It may not describe an absolute beginning, only a threshold where the laws we know cease to apply. Physicists continue to explore how the earliest conditions could have produced the universe we see today. Some propose that quantum fluctuations in the primordial vacuum gave rise to spacetime itself. In this view, the universe did not emerge from nothing, but from a quantum potential where nothingness had structured a state governed by uncertainty and probability. A brief fluctuation could have produced a patch of spacetime dense with energy, and if that energy drove inflation, it would expand into the vast cosmos we inhabit. In such models, creation is not a single miracle, but a natural outcome of quantum laws. Others propose that the Big Bang may have been preceded by a contraction, a previous universe collapsing in on itself until quantum effects caused it to rebound. This idea, known as the Big Bounce, replaces the singular beginning with a cycle of cosmic birth and death. Evidence for such a bounce might be hidden in subtle asymmetries of the cosmic microwave background or in gravitational waves left over from earlier cycles. If proven, it would suggest that the universe has no absolute beginning, only an eternal rhythm of expansion and contraction. Even more speculative are models where the universe emerges from higher dimensional spaces. In some string theory frameworks, our universe could be a three-dimensional brain floating in a higher dimensional space, and the Big Bang could represent a collision between such brains. These ideas remain far from verification, but they show how deeply the mystery of the beginning has forced science to expand its imagination. The further we press toward the origin, the more our concepts of time, space, and causality begin to blur. For now, the Big Bang remains our best map of cosmic history, a map that starts not with nothing, but with everything condensed into a single, radiant potential. It describes how the first atoms formed, how gravity sculpted the first stars, and how galaxies emerged from chaos. It explains why the universe is expanding, and why that expansion continues to accelerate under the influence of dark energy. It gives coherence to everything we observe. But it also reminds us that the map is not the territory. The singularity at the heart of the model is not a place. It is a symbol of our ignorance, a mathematical signal that our tools are incomplete. That recognition that the Big Bang is both a triumph and a boundary is what keeps cosmology alive. Every generation of scientists reaches the edge of the known and realizes that the edge is not a wall but a horizon. Just as Copernicus displaced Earth from the center of the universe, and Einstein displaced time from its absolutes, modern cosmology displaces the idea of a knowable beginning. The origin of everything may lie forever beyond what we can measure, yet that does not make it unreachable. The pursuit itself expands our comprehension, not by eliminating mystery, but by refining it. The philosophical implications are profound. If time itself began with the universe, then the question, what came before, loses meaning. Cause and effect, the foundation of scientific reasoning, may not apply at the moment of creation. The Big Bang marks the boundary where human language, shaped by experience within time, ceases to describe reality. Beyond it lies a domain where physics and metaphysics meet, a reminder that understanding the universe is not only a technical problem but a conceptual one. Still, the scientific approach persists precisely because it acknowledges those limits. By admitting what it cannot yet explain, science maintains its honesty. The Big Bang is not the final word. It is a living hypothesis, constantly refined by new evidence. Its boundaries are not failures, but invitations, places where the next discoveries will emerge. The story of the Big Bang, then, is not a story of an explosion that happened long ago. It is the story of a universe still expanding, still cooling, still unfolding its complexity from the simplest of beginnings. It is also the story of our own curiosity, reaching backward in time to understand what it means to begin. The Big Bang remains our best story, but it begins with equations that no longer work. To move forward, we must question the very origin of time itself. If the Big Bang defines the beginning of space and time, Einstein's theory of relativity defines their behavior. It has guided our understanding of gravity for over a century, surviving every test, yet still breaking down at cosmic extremes. To grasp where our understanding falters next, we must examine the fabric itself, space-time, and the cracks that are beginning to show. When Albert Einstein published his general theory of relativity in 1915, he reshaped our view of reality. Space and time, once thought of as separate and absolute, became part of a single fabric space-time. This fabric could bend, stretch, and ripple in response to mass and energy. Gravity, in Einstein's hands, ceased to be a mysterious force and became geometry itself. The Earth orbits the Sun not because it is pulled by an invisible tether, but because the Sun's mass curves space-time, and the Earth follows the straightest possible path through that curve. Over a century later, relativity still stands as one of humanity's most extraordinary intellectual achievements. It predicts the bending of starlight around the Sun, the slowing of time near massive bodies, and the stretching of light into red as it escapes gravity's grip. Each prediction has been tested with exquisite precision and confirmed again and again. Without relativity, satellites that rely on atomic clocks, including those powering the global positioning system, would drift kilometers off course each day. The theory is not abstract. It is woven into the technology that guides us. In 2015, another of Einstein's predictions was confirmed when the Laser Interferometer Gravitational Wave Observatory detected ripples in space-time itself, gravitational waves produced by the merger of two black holes over 1 billion light-years away. That signal, lasting only a fraction of a second, was the faint echo of the most violent events in the cosmos. It proved that gravity is not instantaneous, as Newton imagined, but travels as waves, moving at the speed of light. Relativity had once again survived the most demanding of tests. And yet, even as every experiment reaffirms it, relativity also reveals its limits. The cracks do not appear in its predictions, but in its incompleteness. Einstein's equations describe the large-scale structure of the universe with elegance, but they fail entirely at the smallest scales. When applied to the quantum realm, where uncertainty and probability rule, relativity breaks down. Its smooth geometry cannot coexist with the jittering, discontinuous nature of quantum mechanics. The most dramatic failures occur where gravity is strongest inside black holes and at the beginning of the universe. In these extremes, space-time collapses into singularities, regions where density becomes infinite and the equations cease to make sense. These singularities are not just unknown, they are unknowable within the framework of relativity. They signal that the theory, for all its success, cannot be the final word. Physicists have spent decades searching for a deeper framework that unites relativity and quantum mechanics into a single consistent picture. The quest for quantum gravity has produced many approaches, none yet proven. In string theory, all particles and forces, including gravity, arise from tiny vibrating strings existing in higher dimensional spaces. In loop quantum gravity, space-time itself is quantized, composed of discrete loops that weave together into a network. In both approaches, the continuum of relativity dissolves into a granular structure at the Planck scale, where distances are measured in units of 10 to the power of -35 meters. At that scale, the idea of a smooth fabric of space-time breaks down. Quantum fluctuations churn geometry into a frothing foam. Time and distance lose meaning, replaced by relationships among quanta of geometry. In this picture, space-time is not fundamental. It is an emergent phenomenon, like a surface forming from countless microscopic molecules. Relativity describes the large-scale shape of this surface, but not the underlying structure that gives rise to it. Evidence for such a deeper structure remains elusive, but theoretical hints abound. The study of black hole thermodynamics has revealed that spacetime possesses entropy, suggesting that it is composed of microscopic degrees of freedom. The holographic principle derived from the relationship between black hole entropy and surface area implies that the information content of any region of space is encoded on its boundary. Gravity, then, might not be a fundamental force, but an emergent effect arising from information and entropy. Even more striking are the connections between quantum entanglement and geometry. In recent years, physicists have found that the mathematical structure of spacetime appears to arise naturally from the patterns of quantum entanglement among particles. When two regions of a quantum system share information, they are connected by an emergent geometric link, a bridge in spacetime. If those entanglements vanish, the bridge disappears, and space itself tears apart. In this view, spacetime is literally woven from information. These ideas do not contradict relativity. They complete it. Einstein's equations remain valid wherever spacetime behaves smoothly, but they emerge as approximations from a deeper quantum foundation. Just as Newton's laws survive within relativity as special cases, relativity may survive within quantum gravity as a macroscopic description of a more intricate microstructure. The challenge of modern physics is to identify that deeper layer and describe its rules. Even without a full theory of quantum gravity, relativity continues to guide our exploration of the cosmos. The first image of a black hole's shadow, captured in 2019 by the Event Horizon Telescope, perfectly matched the predictions of Einstein's equations. Space and time bend exactly as his mathematics described up to the very edge of the unknown. Inside that edge, however, we still do not know what happens. The center of a black hole remains a place where our best theories collapse. The same is true for the Big Bang. Relativity describes the universe's expansion and evolution, but not its origin. As the clock rewinds toward the first instant, the equations break down, yielding infinities. Time itself, as relativity defines it, may have begun not at a moment, but at a boundary where the theory loses meaning. To go beyond that boundary requires a quantum understanding of spacetime. The cracks in relativity are not flaws to be fixed. They are doors to deeper truth. They remind us that even the most successful theories are provisional. Einstein himself suspected this. Late in his life, he searched for a unified field theory that would reconcile gravity with electromagnetism. He did not find it, but the search continues in the same spirit. The belief that the universe is coherent, that every apparent contradiction is an invitation to greater understanding. Relativity remains the most precise description of gravity ever conceived. Its predictions have withstood a century of scrutiny, but beneath its elegance lies a mystery that it cannot solve. What is spacetime made of? If it bends, stretches, and vibrates, it must possess some internal structure. Somewhere beyond our current reach, the equations that describe that structure await discovery. If spacetime itself is not fundamental, then what truly builds reality? The search for that answer defines the next frontier of physics, a frontier where geometry, gravity, and quantum information converge. At the heart of modern physics lies a revelation as radical as any in human thought. The universe, at its most fundamental level, is not deterministic but probabilistic. The laws that govern atoms and particles do not predict precise outcomes, only the likelihoods of different possibilities. Reality, in this view, is not a clockwork of certainty, but a field of potential, waiting to be realized through observation. This understanding began in the early 20th century, when experiments shattered classical expectations. Light, once thought to be a wave, behaved like particles. Electrons, once thought to be particles, behaved like waves. In the famous double-slit experiment, electrons fired one at a time, through two slits, produced an interference pattern, evidence of wave-like behavior, until a detector was placed to measure which slit they passed through. Then the interference vanished, and the electrons acted like particles again. The act of measurement changed the outcome. Erwin Schrödinger's equation captured this strange behavior mathematically. It describes how a quantum system evolves, not as a definite object, but as a wave function, a cloud of probabilities, representing all possible states. When a measurement is made, the wave function collapses to a single value. Before that, the system exists in superposition, not one thing or another, but many at once. Werner Heisenberg's uncertainty principle made this indeterminacy explicit. The more precisely one measures a particle's position, the less precisely one can know its momentum, and vice versa. This is not a technical limitation, but a fundamental property of the universe. Nature itself does not assign both values simultaneously. Reality, at the quantum level, is inherently incomplete until observed. Albert Einstein resisted this conclusion. God does not play dice with the universe, he said. But decades of experiments have proven that the universe, if it plays dice, does so with perfect consistency. In the 1960s, John Bell derived a theorem showing that if quantum mechanics were incomplete, if hidden variables determined outcomes, then certain statistical correlations between entangled particles would not appear. Experiments have confirmed those correlations repeatedly. Quantum entanglement is real, and it violates the classical notion of local causality. Entanglement reveals that the universe is profoundly interconnected. When two particles interact, their properties become linked, no matter how far apart they travel. Measuring one instantly determines the other. This is not communication faster than light, but a reflection of shared information. The two particles are no longer independent. They are part of a single quantum system. Reality is not composed of isolated objects, but of relationships. Despite its strangeness, quantum mechanics is the most successful theory in science. Its predictions have been verified with astonishing precision, from the energy levels of atoms to the behavior of semiconductors. Quantum electrodynamics, which unites quantum mechanics with special relativity, can predict the magnetic moment of the electron to 12 decimal places. The accuracy of these results defies comparison with any other field of knowledge. Quantum theory also defines the limits of what can be known. It tells us not only what can happen, but what cannot be determined in principle. The world is not a fixed stage on which events unfold, but a probabilistic tapestry in constant flux. The outcome of any experiment is not predetermined. It is drawn from the probabilities encoded in the wave function. Reality, at its smallest scales, is statistical. The implications extend far beyond the laboratory. Quantum mechanics explains the stability of atoms, the behavior of stars, and the chemistry of life. It governs nuclear fusion in the sun and the flow of electricity in every device. The world of the everyday is built upon quantum uncertainty, averaged into predictability. Classical physics emerges from quantum law the way smooth water emerges from the motion of countless molecules. Yet the philosophical questions remain profound. What does it mean that reality exists only as probability until measured? Does the act of observation create the world we see, or merely reveal it? Theories differ. The Copenhagen interpretation holds that measurement collapses the wave function into a single outcome. The many worlds interpretation claims that all possible outcomes occur, each in its own branch of the universe. Other approaches, pilot wave theory, relational quantum mechanics, cubism, attempt to reconcile the mathematics with different notions of reality. None can yet claim final authority. Still, all interpretations agree on the same core truth. The universe behaves according to probabilities, and those probabilities are real. The laws of physics do not predict events with certainty. They assign them likelihoods that play out statistically across time. This is not randomness in the ordinary sense. Quantum mechanics is not chaos, but order expressed through probability. Even the arrow of time may arise from quantum processes. When particles become entangled and then decohere, losing their quantum correlations to the environment, the process is irreversible. Each interaction increases the spread of information, just as entropy increases in thermodynamics. Time, in this view, is the accumulation of quantum measurement, the universe continuously updating its own state. quantum mechanics also unites with information theory in unexpected ways. The wave function itself can be interpreted as a carrier of information, a record of what can be known about a system. When that information changes, the physical world changes with it. Reality becomes an informational process, not a static structure. The most fundamental event in nature is the transfer of information from one system to another. This idea leads to profound unity. The same mathematics that describes the entanglement of particles also describes the geometry of spacetime and the entropy of black holes. The boundaries between quantum mechanics, gravity, and thermodynamics blur into a single informational framework. The universe behaves like an interconnected network of probabilities, constantly computing its own evolution. The quantum universe is therefore not unknowable but endlessly surprising. Its unpredictability is not confusion but creativity, the source of diversity and structure in everything from atoms to galaxies. The uncertainty that limits our predictions is the same uncertainty that allows complexity to exist. At its core, quantum mechanics teaches that truth is not static but dynamic, not singular but statistical. The universe does not unfold with certainty, it unfolds with possibility. And within those possibilities lies everything that ever was or could be. The universe, at its most fundamental level, obeys probability, not certainty. But that does not make it less real. It makes it alive. For most of scientific history, the physical universe was understood as a stage, a vast arena filled with matter and energy, governed by immutable laws. But the deeper physicists have looked into that stage, the more they have found that the stage itself is not what it seems. The fundamental substance of reality may not be matter or energy at all. It may be information. This is not metaphor or mysticism. It arises from direct, evidence-based inquiry into how nature behaves at its smallest and largest scales. Every particle interaction, every quantum event, every gravitational field obeys relationships that can be expressed as exchanges of information. When physicists describe the state of an electron or a galaxy, they are not describing what those things are, but what can be known about them, the probabilities, correlations, and entanglements that define their behavior. Reality, it turns out, is inseparable from the information it contains. The modern understanding of this idea began with Claude Shannon, who in the mid-20th century defined information not as meaning, but as a measure of uncertainty. The more possible states a system could have, the more information it carried. This abstract insight quickly found its way into physics. Rolf Landauer later showed that information is physical, that erasing a single bit of data produces a measurable amount of heat. From that realization came a profound truth. Every computation, every measurement, every interaction in the universe consumes and transforms energy. Information, energy, and entropy are bound together by the same laws. This relationship is nowhere more striking than in the study of black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy, a measure of the information they contain. A black hole's entropy is proportional not to its volume, but to the area of its event horizon. This revelation implied that all the information about what falls into a black hole could be encoded on its surface. That surface, the horizon, acts as a boundary of information. From this insight grew the holographic principle, one of the most remarkable ideas in modern physics. Proposed by Gerard Hooft and Leonard Susskind, it suggests that the total amount of information in any region of space can be described by data inscribed on its boundary. In other words, the three-dimensional world we experience may emerge from information encoded in 2 dimensions. The mathematics of this principle have been confirmed in the anti-de Sitter, divided by conformal field theory correspondence, discovered by Juan Maldacena in 1997, which shows that a gravitational theory in a higher dimensional space can be perfectly equivalent to a quantum theory without gravity on its lower dimensional boundary. Reality, at least in these models, behaves like a hologram. The implications are staggering. If space and gravity can emerge from patterns of information on a surface, then space-time itself is not fundamental. It is a manifestation of quantum entanglement, the way information is shared between particles. The smooth geometry of the universe, the curvature that Einstein described as gravity, may arise from networks of entanglement at the quantum level. Where information is dense and correlated, space appears curved. Where entanglement weakens, distances stretch. The fabric of space-time becomes a reflection of information flow. This view also reshapes how we think about observation. In quantum mechanics, to observe is to interact, to exchange information. The wave function, that strange object describing a system's potential states, collapses when information about the system becomes definite. Observation does not create reality. It updates the information we have about it. The universe is not a static collection of facts, but a dynamic process of information being continuously refined through interaction. Information theory provides a unifying framework for seemingly separate domains. Thermodynamics, quantum mechanics, and gravity all obey the same informational logic. Entropy in thermodynamics measures missing information about microscopic states. The second law, that entropy increases, means that information spreads and becomes harder to recover. Quantum theory measures uncertainty in terms of information probabilities. General relativity can be interpreted as describing how information density determines the shape of space-time. What began as an abstract branch of mathematics has become the most fundamental language of physics. Modern research reinforces this unity. Quantum computers manipulate information directly at the level of quantum states, exploiting superposition and entanglement to perform computations that would take classical machines longer than the age of the universe. The same principles that make quantum computing possible, coherence, measurement, and decoherence, describe how information behaves throughout the cosmos. The universe itself may function as a kind of natural quantum computer, continuously processing its own state. Even time can be understood as an informational phenomenon. The arrow of time, the difference between past and future, is tied to the growth of entropy, which is the spreading of information. The universe moves forward in time because information disperses. It never flows backward, because information cannot be perfectly unerased. What we experience as time's passage may be the universe's ongoing computation, the continual updating of its informational state. If information is truly the foundation of reality, then matter and energy are secondary, emergent expressions of data relationships. Observation, interaction, and entanglement are not byproducts of physics. They are physics. Existence becomes a vast network of informational exchanges, each moment a new configuration of what can be known. This vision changes nothing about the empirical success of physics, yet it deepens what those successes mean. It tells us that to study the universe is to study the way it encodes, processes, and reveals information. It also reminds us that knowledge and reality are intertwined, that what can be known and what exists are part of the same structure. If the universe is built from information, then knowledge itself participates in the act of creation. Each measurement, each discovery, each refinement of understanding adds to the ongoing computation that defines existence. The cosmos is not a thing. It is a process, a continuous conversation between what is and what can be known. If the universe is built on information, then perhaps knowledge itself shapes its structure. The more deeply science explores the universe, the more it encounters boundaries, not walls of ignorance, but horizons built into the nature of reality itself. Knowledge, like space, has a shape. It expands through discovery, but it is bounded by principles that no mind or machine can overcome. The first of these boundaries is cosmic. Because light travels at a finite speed and the universe has a finite age, there is a limit to how far we can see. The cosmic horizon, about 46 billion light-years in every direction, marks the edge of the observable universe. Beyond it lies a realm from which no signal can ever reach us, no matter how long we wait. This is not a technological limitation, it is a structural one. The universe hides its totality behind the curvature of spacetime itself. There are smaller but equally profound limits in the quantum world. Heisenberg's uncertainty principle tells us that certain pairs of quantities, position and momentum, energy and time, cannot both be known precisely. The more we know one, the less we can know the other. This is not due to imperfect instruments. It is built into the fabric of existence. Nature itself withholds exactness. The world is not made of definite states waiting to be discovered, but of probabilities waiting to be realized. Mathematics, too, imposes limits on what can be known. Kurt Gödel's incompleteness theorems prove that in any logical system capable of describing arithmetic, there exist true statements that cannot be proven within that system. There is no ultimate self-contained description of truth. Physics, which rests upon mathematics, inherits this incompleteness. No matter how elegant a theory becomes, it will always rest upon assumptions it cannot justify from within itself. Even the structure of spacetime places constraints on knowledge. The Planck scale, about 10 to the power of minus 35 meters, marks the smallest meaningful distance. Below it, the very concepts of space and time break down. At that scale, quantum fluctuations overwhelm geometry, and no experiment can reveal what lies beneath. The same is true of the Planck time, about 10 to the power of minus 44 seconds, the smallest tick of the cosmic clock. The universe itself resists finer measurement. These boundaries also define the limits of information. The holographic principle implies that any region of space can contain only a finite amount of information, proportional to the area of its boundary. The cosmos, vast though it is, has a finite capacity for detail. No physical process can exceed this informational density. The universe, in a profound sense, is finite in what it can know about itself. There are human limits as well. The human brain, remarkable as it is, can store only so much information, comprehend only so many dimensions, visualize only so many scales. Our senses evolved to navigate a narrow band of phenomena, temperatures, speeds, and distances suited to survival on one planet. The rest we must infer through instruments and imagination. Even those tools, however advanced, are extensions of our limited cognition. But limits do not mean futility. They are the structure within which discovery occurs. The boundaries of knowledge define the shape of inquiry, giving direction and purpose to exploration. The speed of light, the uncertainty principle, the cosmic horizon. These are not obstacles, but coordinates of understanding. They show where knowledge ends and wonder begins. Science's strength lies in acknowledging these limits. Every great advance in physics has come from confronting the edge of the knowable, from realizing that a cherished theory breaks down and must be rebuilt. When Newton's mechanics failed to describe Mercury's orbit, relativity was born. When relativity and electromagnetism clashed at atomic scales, quantum theory emerged. Progress comes not from pretending the limits do not exist, but from asking why they are there. Perhaps the deepest boundary of all is not physical but conceptual. Science can describe what the universe does, but not why it exists. It can reveal how stars form and galaxies evolve, but not what gives being itself to the laws that govern them. Such questions why there is something rather than nothing, or why mathematics describes reality so perfectly may never yield to empirical method. They belong to reflection, to philosophy, to the awe that lies beyond measurement. The limits of knowledge are not defeats. They are the conditions that make knowing possible. A universe with no boundaries would have no structure, no patterns to discern. The unknowable is not the end of science, but its horizon, the line that recedes as understanding grows. Perhaps the only absolute truth is that complete knowledge will forever remain beyond our reach, and that is what keeps science alive. Science endures because it embraces error. Every discovery begins with the recognition that what we believed yesterday is no longer sufficient today. The beauty of science is not that it is right, but that it knows how to be wrong productively. Through error, understanding evolves. History shows this pattern again and again. The Ptolemaic system of epicycles explained the motion of planets with impressive precision, yet it was wrong. Copernicus placed the sun at the center and revolutionized astronomy. Newton's laws described motion so accurately that they seemed final until Einstein revealed that space and time themselves bend under gravity. Quantum mechanics shattered the determinism of classical physics and replaced it with probability. Each step was a correction, not a destruction, of what came before. Science does not discard the past, it refines it. This self-correcting nature is science's defining virtue. A theory must be falsifiable, open to being proven wrong, or it is not science at all. Dogma seeks confirmation, science seeks contradiction. Theories survive not because they are unassailable, but because they continue to match observation better than their rivals. When they fail upward, pointing the way to new understanding. Being wrong is not shameful, it is inevitable. Theories are maps, and all maps are incomplete. They work because they approximate reality closely enough to be useful, not because they capture it fully. Every experiment tests the distance between model and world, and every failure narrows that gap. This humility is not weakness, it is strength. Science advances not by pretending certainty, but by admitting uncertainty. Each correction strengthens the structure of knowledge. The universe does not conform to our expectations, we conform to its evidence. Technology magnifies this process. New instruments do not merely confirm old ideas, they expose their limits. Telescopes reveal galaxies we did not know existed. Particle colliders uncover particles we did not predict. The James Webb Space Telescope now shows galaxies forming earlier than our models allowed, forcing cosmologists to reconsider the timeline of cosmic evolution. Every discovery redefines the boundary between what we know and what we must learn anew. To redefine truth in this way is to see it not as a fixed point, but as a moving horizon. Science does not seek finality, it seeks better approximation. Each generation revises the universe's story not because the old stories were false, but because they were incomplete. At its deepest level, this is not only a method of knowledge, but a philosophy of humility. To be wrong is to be teachable. To revise one's view is to evolve. Science succeeds not despite its errors, but because of them. We do not uncover the universe's final truth. We simply sharpen our questions, and each answer brings us closer to wonder.